Hey everyone, we're in our next session. I have Shawn here, another one of our software developers who'll be doing benchmarking your runtime. I guess you've got your title. Yeah, I'll let you take it from here.
All right, cool. Hello, everyone. Okay, I have a lot to cover, so I'll be trying to move things through kind of quickly. First, I already apologize in advance. If you don't know, and you haven't heard me talk before, I talk quite fast, and I know it, and I'll try to keep it nice and slow. Yeah, when we talk about benchmarking and kind of how you can basically use it and how it works in Substrate, this will be kind of an advanced talk. We can do the overview, but this is gonna be an advanced talk. It's gonna be targeted mostly towards people who are familiar with building on Substrate, who are familiar with Frame, who've already done a bunch of programming. And benchmarking is kind of one of the last steps in your development process. And it basically helps you get your idea into something that's production ready, something that is safe to use on a network. And so really I'm trying to target people in this talk who are at that stage, who have built their awesome ideas, their awesome palettes, and are ready to benchmark and kind of want to understand how exactly that works. So to give you an overview of what I'm going to be talking about today, we're going to do a quick recap of weights. We're going to actually dive deep into benchmarking, exactly how it works. I'm going to be talking about some of the things we learned throughout development, things that I think will inform you about in kind of decisions we made and some things to keep in mind. And finally, some best practices and common patterns. So yeah, let's jump right into it. Okay, first, what is weight? So if you attended the last Sub0, Gav actually gave a great presentation, much deeper into weights and kind of the weight system in Substrate, and definitely recommend you look at that. We have a few resources also online, but just a very high level overview. Weight is basically a representation of block execution time. So you might know in any blockchain, there's a kind of a target block time. I think Substrate by default has a block time target of around 6 seconds. And so in that 6 seconds, there's a limited amount of computation you can do. And so weight is kind of representation of that time and the time that you can spend doing computation. So built into Frame, we have this hard-coded that 10 to the 12 weight is equal to 1 second, or 1,000 weight is equal to 1 nanosecond. And so really, when we talk about weight, we're really just talking about some other representation of time. And so let's kind of take a look at what weight might look like for an average block. So again, assuming that we have a 6-second block time, our block can be composed of some amount of computation. You'll see that in this diagram here, we don't actually use all 6 seconds for computation. We actually only use about 2 seconds of the 6 seconds for actual execution of your block. The rest of it we leave for buffer for things like propagating your blocks across the network or any other kind of unforeseen situations. So basically, within the 6-second block, we actually have a smaller window of time to actually do computation. And this computation are things that you're probably all familiar with. Things like, importing a block, the block import overhead, uninitialized functions, the extrinsics that are inside of your block, and on-finalized, stuff like that. And so basically, what is the amount of computation, what amount of logic that we can execute in this 2-second window? And what is kind of the mechanism we use to measure and keep track of how much we can actually get done in this time period? So one thing that you might be thinking is, well, how can weight represent 1 second? Like computers are different, right? And well, this is very true. And weight is actually specific to each blockchain. So as you can imagine, if you have a more powerful computer, the amount of computation you can do in 1 second is more. And if you have a weaker computer, it's less. So really, when we're talking about weight, each blockchain, each substrate chain that you develop will have its own notion of what exactly weight means. So you could be using the same palette on 2 different blockchains, and they could have different weights, which are both correct, but correct for the blockchain at hand. And one of the things to note is that weights will evolve over time. So again, as time goes on, computers get faster, software changes, your code changes, and so these weights in your blockchain will evolve over time. And this is one of the challenges we had to overcome when doing benchmarking, making things simple to update, making things easy to find out what the actual weight values are for your current system. And of course, I think a lot of people always ask in Substrate, like, what are the transactions per second, or in Polkadot, how many transactions per second can you get, and how much throughput can you get? And I kind of find this to be kind of a silly question, because when we talk about transaction throughput, this depends on a lot of assumptions. And let me just look at the list of assumptions I have here. What kind of processor you're running, what kind of memory, hard drive things you have, what operating system you're using, what Rust compiler you're using. All of these things can affect your transaction throughput. So if I'm running my blockchain on my phone, or Raspberry Pi, for example, you can't expect the same kind of throughput that you would get if you're running it on a dedicated server with tons of cores, tons of basically hardware specs, right? But and you can get crazy numbers when you talk about these crazy hardware specs. If you have a supercomputer running your blockchain, of course you probably achieve maybe like 10,000 transactions per second. But what it really means though is that validators in your network have a very high bar of entry. Like when we try to build all this weight and benchmarking stuff, it's to try to keep your network safe from attacks and keep your validators doing their job correctly. And so the more restrictions we place onto the hardware requirements, basically the more limitations we put onto the validators who can actually validate your pool. So when you're making decisions about kind of what hardware to use and what kind of throughput you're targeting, you need to make these kind of decisions in mind. So yeah. So let's jump right into it. The benchmarking framework, what kind of tools it provides, and how it works. So basically, what is the benchmarking plan? So our plan was to do empirical measurements of the runtime to determine, excuse me one second. Empirical measurements of the runtime to determine how long it takes to do certain things. So I think there are other approaches you could take to doing benchmarking, definitely much more theoretical stuff, maybe like, measuring the operations and doing, something like gas metering. But when it comes down to it, and as Gav has mentioned here, that gas metering has a lot of overhead. And so what we want to do here is basically, there's a lot of parameters and variables which should affect how your benchmarking runs. So really, we want to treat benchmarking as kind of like a black box. We just want to execute exactly the same way that you would execute your blockchain when you're running it, and just measure the timings and try to understand, okay, well, how long do these functions take, empirically? And so ultimately, one of the things we have to make sure is that we're running these benchmarks in generally worst case scenario conditions. So it's not about the green field scenario. With benchmarking, we want to make sure that we're protecting ourselves from attackers, and attackers are going to take advantage of worst case scenario situations. So one of the assumptions we make with the benchmarks is how can we test these different scenarios in the worst case situation. And remember, the primary goal of benchmarking is to keep the runtime safe. It's not to gloat about our TPS or gloat about our throughput. It's basically to make sure that what we launch to a decentralized open network is safe. And secondarily, we then want to say, okay, well, how can we make sure that these weights are as accurate as possible, the benchmarking is as accurate as possible, so that we can get the maximum throughput possible while maintaining safety. Yeah. So then part of the framework, basically, it all starts with this macro. So we built this benchmarks macro, which is a part of Frame, just like the other macros you're familiar with, building your palettes. This macro basically allows you to set up different benchmarks. And you can see here the structure of it is quite simple. We have this benchmarks macro, where basically you pick an extrinsic, you have some code which sets up the initial state of that of what you want to benchmark, then a piece of line where it basically executes that function or that extrinsic, and then a verify block where you can basically verify the final state. And really, the benchmarks macro acts like you're writing a runtime test. Basically, you're just setting things up, executing your function, and verifying that it all worked as you expected. And when you write these benchmarks, we basically directly integrate into the rest of the system to be able to run these benchmarks through our Frame benchmarking platform. So built into this platform is also this multiple linear regression analysis. So one of the assumptions we make on top of Substrate is that none of the functions, none of the extrinsics actually have superlinear complexity. We assume that everything is of linear time or less. And so what we're able to do is then during the benchmarks, we're able to run these functions, get timings, and then look at how the function behaves over different timings. And actually basically do regression analysis to determine, okay, what is the slope of this line, or how can we predict, given any inputs, what the function's time would take. And so it looks something like this. And of course, the crate we're using, this linear regress crate, supports multiple linear coefficients. So you can have a function which is dependent on multiple different factors, and we can determine, kind of how that function should behave given any input. And there are some functions which have no inputs. There are some functions that are completely constant time. In that situation, we basically use the median value. It's important to use the median and not like the mean, because the median is not susceptible to things like outliers, where the mean, if you have like some kind of random outlier computer, stalled for a second while doing the benchmark, could really skew the results of your benchmarking. Okay. Okay, and then another piece of this benchmarking framework is basically this benchmark CLI. So once you've kind of written everything, we actually unlock this benchmark CLI behind a feature flag. So when you compile your node, you can compile it with this feature flag, features runtime benchmarks. And if you do this, then you get access to this CLI. And the CLI basically allows you to really easily run your benchmarks. And I'll kind of go into that a little bit later. But this is where a lot of you can help, because you all try to benchmark your runtime can actually use the CLI and give feedback on what kind of features you want. You can imagine that this CLI is quite still, it's still in a lot of development. So, there's a lot of features I'm sure people will be asking for, and please, you can give feedback. Then there's this auto-generated weight info. So once you've ran the CLI, basically we generate for you a file, and the final output of the benchmarking process is just a Rust file. And this file implements what we call a weight info trait. And basically this weight info trait is just a set of functions which define what the weight of your extrinsic should be. So you can see here I have a weight info for the balances palette. You can see here there's a separate function which tells me the weight of each of the extrinsics that you can call in the balances palette. So what's nice here is that this file is something that's configurable and external to the actual palette. So as I mentioned, each blockchain is different. So when you run the benchmarks on your blockchain under your scenarios, we'll generate a unique weight info file for your blockchain, which you could integrate into your palette, and you can configure exactly however you want. So Polkadot has a file which has a bunch of weight information in it, but your blockchain will probably have a different set of information using the same palettes that we both use. And this is, again, really making these palettes as modular and extensible as possible and usable on any blockchain, no matter kind of what the assumptions are. And this weight info trait is ultimately designed to make the automation process really easy. And we'll kind of show you some of the automation process later in this presentation. Cool. Okay, so let's actually get into the deep dive. I'm going to walk you through the benchmarking process and kind of show you what happens during a benchmark. Okay, so these are the steps. There are 10 steps, basically, we run through to actually do a benchmarking. And if you want to, you can actually follow these steps, through the code by going into this frame benchmarking librs file. There's a function called run benchmark, and it basically is a code version of this table here. All right, so the first step is we whitelist known DB keys. So one of the things you have to note in benchmarking is that database operations, database reads and writes are expensive. And so it's important that we track how many database operations you're doing in your benchmark. But not all operations are expensive per se. If you actually listen to my talk maybe 2 Sub0s ago, I have a really deep dive talk into storage. You would know that the expensive part of reading storage is actually accessing the value in the Merkle tree. You have to basically traverse the Merkle tree to get access to that value. Once you've accessed that value once, it lives in this storage overlay, and it lives in the storage overlay for an entire block. So there are certain storage items which every single block will always access. Things like the block number. Every single block, the block number will change. So if you write some runtime code which reads the block number, it's not per se expensive because it's already in this overlay cache. So one of the things we want to make sure is when we're doing the benchmarks that we take into account all of the storage items which you think for your blockchain should be kind of ignored from the benchmarking process. That shouldn't be counted as a overhead. And you can, of course, configure this. But some examples are things like block numbers, events, total issuance. These are all things that kind of change every block anyway, right? So these are things that we ignore when we run benchmarking. You can configure your own whitelist to ignore different database keys to basically make sure that your benchmark represents the least possible time, which is still safe. And there's also a whitelisted account. So another good example of a whitelisted storage item is actually an account. So when I'm doing a transaction to my runtime, there are things already changing about my account, like the balance for the fees they take, the nonce that increases. So my account, when I'm calling into the function, also already has changed. So if you have a runtime function which changes something else about the account or reads something about the account, that's already free too. So this is all kind of part of this whitelisting process. Okay, and then we have a benchmark, and a benchmark is composed of these components. Components are the factors which can affect how the benchmark behaves, right? So you can imagine that a function which changes the members of a group could be affected by how many members there are in the group. The more members, maybe the more complex the function gets. So you can imagine in general like a function with like 3 components, 3 variables which affect the weight of that function. Basically what we want to do is we want to check benchmark our function over different values of these components and try to understand, okay, what are the weights at these different values? So we'll have these components like X, Y, and Z, they're just examples, and they'll have some range, like, X can vary between 0 and 5, Y can vary between 0 and 10, etc. And basically from this, we will generate a table of values where we're gonna benchmark all of these different vertical columns. And so we'll run a benchmark with the value X equals 0, Y equals 10, Z equals 1. And we'll run another benchmark with X equals 1, Y equals 10, Z equals 1. And do all of these benchmarks to understand, all the data points for our benchmark. You can see here, this is a little bit interesting. So one of the things we do here is we allow you to configure the number of steps you want to take. So you can tell the benchmarking system how many samples you want to take in each of these components. But it's just kind of an implementation detail. I don't want to go too deep into this. Is that you'll see here that even though I'm saying to take 3 steps, that the number of steps I actually take may vary depending on how large the range is. For example, if I have 5 values, it's not really easy to take 3 equal steps. So you see the resolution here actually becomes that I'll take 5 steps here, 3 steps here, only 1 step here. Implementation detail, maybe not super important, but something I just wanted to point out if anyone was confused about these diagrams. Yeah, so then we'll actually go and run the benchmark. So now that we have this table, like we have all the different inputs we want to test, now we'll actually test the benchmark. And so basically what we'll do is we'll run this block in your benchmarks macro, this setup initial state, and we'll basically set up the initial state depending on however you want. And of course, your benchmarks have access to these component values. So it may be that you want to say, okay, I want to run a benchmark where the number of members is 10 members. So we'll set up the initial state to be 10 members, and you can have access to that variable and basically run any code you've written to set up that state for that component. And one thing we do is we actually commit this to the database and clear the cache. So again, if you remember, everything we're doing here is worst case scenario. So one of the worst case scenarios is that the DB cache is not populated, that the data is committed to the DB state, and you have to access the merge tree to get access to it. And so this is something that we do in the benchmarking. Then the next step is obviously just running the benchmark. So once we've set up the initial state, all we do is basically call our function. So it can be an extrinsic or a function. We basically get the system time, we call the function, and we get the system time again. And basically the difference of these 2 system times is what we say is the time it took to execute this function. We know that there's a little bit of overhead involved with calling the system time, and there's a little bit of inaccuracy there. But we found that this overhead is minimal compared to the actual time it takes to run these extrinsics. So this is not really a large factor in terms of showing up in the weights. So once we run our function, we have a difference in time. We know about approximately how long it takes to run this function. The next thing we do is we also want to count the number of DB reads and writes. So again, I kind of mentioned this already, but the database operations in your blockchain are quite expensive. And so it's important that we really accurately measure how many reads and writes your extrinsic took. And so we have a special database which basically tracks which storage keys you are reading and writing from during the benchmark, and basically track and count the number of keys. If you read from a value twice, we only care about the first read. Like the first read is expensive. The second read is basically what we consider free. And if you write to a storage item, we would consider reads to that item, basically free already, because you've written to the storage item, we're written to the overlay. You don't have to access the Merkle tree to read that data back. So our tracker in our special database basically takes into account all of these actions and gives you an accurate representation of how many first reads or first writes your benchmark took. And finally, we have all of this gets clumped up into some data, into basically some structs where we have basically a list of results, like, given the components, the inputs, what was the extrinsic time, how many reads, how many writes, and other stuff. And it might be that over time we expand what kind of data we track, and there might be more important factors we want to include. This is something that we can get feedback from. But right now, these are the kind of main components we look at, and we process these data. So those are all the steps of the benchmarking process. So you can kind of see an example here. So benchmarking really is a black box. We have some inputs. You write the black box. That's what the benchmarking macro does. You write what this benchmark does. It processes the components at the certain values and then produces these outputs. And you'll see that we can repeat these steps multiple times to basically get multiple results for any input. What are the outputs? And there's like some range. And basically our goal is to basically isolate the different components variables and basically figure out, okay, what is the linear model for these different benchmarking outputs? So you can see here, in this purple section, we're isolating the X component. Y and Z is staying fixed, but X is changing. And therefore we can look at, okay, well, how does X affect the benchmarking of this function? Same with Y, we're modifying Y here and then modifying Z here. And so we're kind of really gonna get three graphs here telling us about the behavior of our benchmark or of our function. Okay, so I think a good way to really make this concrete is to just take an example benchmark. So to do this, we're gonna be looking at a palette, the identity palette. And specifically, I wanna do a quick overview, just to give you context. If you're not familiar with our identity palette, it's actually something that's available both on Polkadot and Kusama. And allows you to basically have some identity information stored on chain for the user account. Things like your name, your email, your Twitter. And you can actually have a variable number of information. So if you don't want to put your Twitter on the blockchain, you don't have to. So one of the factors that comes into play with the identity palette is how many different pieces of information are you storing there. Another piece of the identity palette is that there's these registrars, and registrars are the ones who can actually verify that your data is good. And there's can be multiple registrars, all of whom can individually look at your data and put their own verification status on your data. So another thing that affects the identity palette is how many registrars there are and how many registrars are being used to basically look at your identity. And finally, identities can also have a sub-identities. Basically, they can have these two-way links where you can have a sub-identity which inherits from the identity that you already have gotten. So the exchange we're going to look at is kill identity. So kill identity basically allows you to wipe your identity clean. So let's kind of walk through the different steps up here. So first, you'll see here that we use a specific origin, a force origin. And this is configurable. So one of the things you need to make sure when you're writing your benchmark is that your benchmark will always succeed. Independent of how users configure this force origin, we need to make sure that to allow your benchmark to always work. So in order to do this, we actually added a special function behind a feature flag, which allows us to get a successful origin here. And this is something that you do in your own benchmarking or your own runtimes, is basically hide special features behind this runtime benchmarks feature flag, just like tests, that these are test utilities which aren't really accessible by the main runtime, but are accessible only when you run benchmarks. You can see that we have these hooks. So there are other parts of your runtime which are configurable, and we don't exactly know what logic will run here. And so it's important to be careful that these hooks are taken care of by your benchmark as best as possible. And if your benchmark can't handle these hooks very well, that there are limitations told to the runtime developers on what kind of things they can actually implement in their own code using your palette to make things work.
Shawn, just a quick heads up. You've gone a bit over time. You're at 23 minutes now, so I'll give you another 2 minutes. Is that okay?
Sure. Okay, sure. I guess, so I won't, so I'll try to speed through this. I think mostly the main chunk of what I want to get done is here. You can see we're breaking down the different components, and we're looking at the different pieces of your extrinsic which need to be isolated and benchmarked. And basically, we want to write a benchmark which isolates those components. So you can see here we have at the top these components, like the number of registrars, number of sub-accounts, number of additional fields, and we basically set up like kind of the ranges of these components. And then we just write basically like a runtime test. We set it up that our state is some initial state. We have some user account that we want to use. We create some of the information that we expect for this user account following our requirements. We set up the registrars, stuff like that. And then ultimately, we just call the extrinsic. We just basically, once we have all the state set up, we just call the extrinsic and just execute it. And when we do that, we actually execute it using the CLI tool. You can see here there's a bunch of flags and kind of configurations you can adjust, but we can see here that basically we're calling palette identity, we're calling the extrinsic kill identity. And when we call this CLI, we're basically running our code and getting these outputs, these graphs, which tell us, okay, what were the results of these different benchmarks? So you can see here for each component, as I mentioned, this is 3 components in this benchmark. There are kind of 3 graphs we're looking at. And you can see here, this is a very good example of a component which has a linear effect on the extrinsic time. And so we look at these different graphs. We also look at the database operations is also producing a graph. And basically, it automatically generates for you, the RCLI automatically generates for you this weight formula, which has all of this analysis already baked into it, and that you can just copy and paste into your code. And it just works. And so basically the last piece I wanted to talk about was basically once we've generated this weight formula, this is automatically generated for you using the benchmark outputs, you integrate it into your extrinsic. And you can do it really simply. So we basically have this weight tag. You're probably familiar with this if you've built some runtime palettes before. But you can basically take advantage of this formula and basically the inputs of this formula to do the weight input integration. So you can see here, we just basically use this function and directly use this as the weight. And then one thing we also do is, we assume in the beginning of a function that your function is running in the worst case scenario. So at the end of your function, what you want to do is actually maybe even refund some weight. So here we have the ability to actually return any weight that wasn't used. And this is something. This is a pattern that you'll commonly see to make sure that your runtime stays safe, but also make sure that the fees and the amount of information you can fit into your block is as most as possible. So here we assume what is the weight of this function in the worst case scenario, and then here we say, okay, well the real weight after we've executed this function is this much. And yeah, so again, I don't have time. I shared my slides on the Discord, and I'm very happy for everyone to look through them and ask me questions. But there's some other slides here which are not so much about the actual benchmark, but some of the steps, some of the things we learned about when going through the benchmarking process, and of course some of the best practices that you should follow when you're running benchmarks. Benchmarking is a quite complex topic, but it's very important for you to do this correctly when you're building runtime, so that it's safe to use in the public, in an open network. And of course, I just wanted to, before I end, just talk about what's next. So I think there's, benchmarking has a long way to go. What we have here works well, but I think there's a lot of room for improvement. So things like better regression analysis, more insight into database operations, improved automation, improved integration into Frame. These are all things that we're looking to do. And definitely if you're interested in the whole benchmarking world, you can definitely contribute. These are kind of things that the hard parts I think were mostly built already. And here we're just looking to make the user experiences kind of better. So I don't really have time for questions, but of course I'll be on the Discord channel, and I'll be very, very happy to answer any questions. And I hope you take a look at my other slides I wasn't able to jump to today.
Great. Thank you so much, Shawn. That was great.
Cool. Thank you.
I'm sorry I wasn't able to give you more time to finish up your talk.
It's okay. It's good.
Cool. We were supposed to have a break now, but since we're running a bit behind time, we're actually going to skip the break and move into the next session. So I'll see you in there with Bjorn. Thanks again.
Bye. See you.